All right, guys, today we're going to work on 6.5, which is trigonometric form of a complex number. Just as real numbers can be represented by points on the real number line, you can represent a complex number. And remember, a complex number just means it has a real and imaginary. So A plus BI as the point AB in a coordinate plane. But this one is going to be on the complex plane. It's basically the same thing. So the horizontal axis is called the real axis. And the vertical axis is called the imaginary axis, as shown below. So we're going to draw a coordinate plane. This is your real axis. This is your imaginary axis. And if we draw 3 up, down, left, and right, this point right here, which is technically 3, 1, is 3 on the real axis, but 1 on the imaginary axis, or just 3 plus I. So if I do another one right here at -2, -1, that would be -2 on the real axis and -1 on the imaginary axis. The absolute value of the complex number A plus BI is defined as the distance between the origin 0, 0 and the point AB. Sorry, you guys, I probably hear my dogs in the background. I apologize. The definition of the absolute value of a complex number, the absolute value of the complex number Z equals A plus BI. The absolute value of A plus BI, which is actually going to be the square root of A squared plus B squared. When the complex number A plus BI is a real number, that is when B equals 0. So if it's 0, it'll take that I off of there and make it just a real number. This definition agrees with that given for the absolute value of a real number. A plus 0I is equal to the square root of A squared plus 0 squared, which is the square root of A squared, which equals A in absolute value bars. Our first example is finding the absolute value of a complex number. We're going to plot Z equals -2 plus 5I and find its absolute value. I'm just going to make my own vertical and horizontal axis. Remember, the horizontal is the real and the vertical is the imaginary. So this is the same thing as plotting -2, 5. So we're going to put it right there. And then to find the absolute value, we're going to do the square root of -2 squared plus 5 squared, which equals the square root of 4 plus 25, or the square root of 29. And you can leave it just like that. You don't have to do any work to it at all. The trigonometric form of a complex number. In section 2.4, you learned how to add, subtract, multiply, and divide complex numbers. To work effectively, with powers and roots. Of complex numbers, it is helpful to write complex numbers in trigonometric form. Consider the non-zero complex number a plus bi. By letting theta be the angle from the positive real axis, measured counterclockwise, to the line segment connecting the origin and the point AB, you can write A equals R cosine theta. Same thing, remember cosine goes with your X value, so that's why it's with the A, because A is like your X or your horizontal. And then B equals R sine theta. And remember that R is what we just found, that absolute value, or the square root of A squared plus B squared. Consequently, you have A plus BI equals R cosine theta plus R sine theta, from which you can obtain the trigonometric form of a complex number. So the trigonometric form of the complex number z equals a plus bi is z equals r times cosine theta plus sine theta I, where a equals r cosine theta, b equals r sine theta, and r is the square root of a squared plus b squared. And the same as the last thing, or the last sections, tan theta equals b over a. The number r is the modulus of z, and theta is called an argument. Of z. The trigonometric form of a complex number is also called the polar form. Because there are infinitely many choices for theta, the trig form of a complex number is not unique. Normally, theta is restricted to the interval 0 to 2 pi, although on occasion it is convenient to use theta less than 0. So it says write the complex number z equals -2 minus 2 square root 3i in trig form. So we're going to start with r. It's going to be the absolute value of -2 minus 2 square root 3i. And again, that's from the other paper. And the way that we fix that is we put it in that distance form of Pythagorean theorem, where we take the -2, square it, and the 2 square root of 3 and square it. And this should be a minus, but again, when you square it, it's not going to matter. -2 squared is 4. -2 squared is 4. Square root of 3 squared is 3. So 4 times 3 is 12. 4 plus 12 is 16. So r is going to be 4. The next thing you're going to do is find the tangent theta equals b over a. So your b is your second number, -2 square root 3 over -2. Your -2's will cancel out and leave you with square root 3. So we're going to use tan theta equals square root of 3 to find theta. How do we do that? Remember, we do tan inverse of square root of 3. And that will give you pi over 3. Since z equal to -2 minus 2 square root of 3i is in quadrant 3. Again, when I graph it on the coordinate plane, -2 and -2 square root 3 is over here. That's your quadrant 3. Your pi over 3 is in quadrant 1. We need to get it quadrant 3. So we're actually going to add 180, or we're going to add pi since it's in radian form. And we get 4 pi over 3. So then to write it in trig form, z is going to be equal to whatever our r is, which is 4, times cosine theta plus 4 sine theta I. Our theta was 4 pi over 3, and we can take this 4 out. So what you're going to see, you can either put the 4 in like I just did, or you can separate it. Cosine 4 pi over 3 plus 4 sine 4 pi over 3 and your I. Oh, sorry, that 4 will not go there because I took it out. Another way that you may write it is they may have the I in front. So one more time, cosine 4 pi over 3 plus I sine 4 pi over 3. All of these are the correct way to write it. You decide whichever one you like. Next example is writing a complex number in standard form. We're going to write c equals the square root of 8 cosine negative pi over 3 plus I sine negative pi over 3 in standard form of a plus bi. This one is really quick and easy. You're going to do the square root of 8. Cosine of negative pi over 3, you're going to use your unit circle and cheat it out on that. And you're going to see that cosine negative pi over 3 is 1/2. You can also use your calculator for that, but your calculator will not give you the other one. So the y coordinate of pi over 3, negative pi over 3, is going to be minus square root of 3 over 2. Don't forget to put your I. When you simplify the square root of 8, this is 2, 2, and 2. So I have a pair of 2's and I left a 2. You get 1/2 minus the square root of 3 over 2i. Your 2's will cancel out. And then you can distribute your square root of 2. So square root of 2 times 1 is square root of 2. Square root of 2 times the square root of 3 is the square root of 6i. And again, I got these from the unit circle. So just use your cheat sheets so that will help you out. Multiplication and division of complex numbers. The trigonometric form adapts nicely to multiplication and division of complex numbers. Suppose you were given 2 complex numbers. Z equals, or Z1 equals R1 times cosine theta 1 plus sine theta 1 I. And Z2, I'm going to write the same thing just with twos. R2 cosine theta 2 plus sine theta 2I. Then the product of Z1 and Z2 is R1, R2 times cosine theta 1 plus sine theta 1I times cosine theta 2 plus sine theta 2I. When you multiply that together, when we distribute, so we're going to multiply here. We got cosine theta 1, cosine theta 2. We have cosine theta 1, sine theta 2I. Cosine theta 2, sine theta 1I. And then last, you're going to have plus sine squared theta 2I. That's not right. Sorry, y'all. Not sine squared. It'll eventually be that way. Let's do it this way. Sine theta 1I, sine theta 2I. Using the sum and difference formulas for cosine and sine, you can rewrite this equation as Z1, Z2 equals R1, R2 times cosine theta 1 plus theta 2, not Q, theta 2 plus I sine theta 1 plus theta 2. This establishes the first part of the following rule. Product and quotient of two complex numbers. So let Z equals the same thing that we wrote earlier. R1, Z1 equals R1 cosine theta 1. Remember I said sometimes they'll put the I in the front. I do not care where you put it, so I'm going to put it in the front this time. Z2 is going to look the same way, just with little twos. So R2 cosine theta 2, I sine theta 2 be complex numbers. Then Z1, Z2 is equal to R1, R2. The same formula we just wrote right here. Cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And again, this is the product. The quotient, Z1 over Z2, will be R1 over R2. And remember, just like our log formulas, when we multiply, it's the same as add. When we divide, it's the same as subtract. So cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So this one is the quotient. I'll give you a second to do that. All right. Multiplying complex numbers, find the product of Z1, Z2. Z1 equals 3 cosine pi over 4, I sine pi over 4, and Z2 equals 2 cosine 3 pi over 4, and I sine 3 pi over 4. So again, we're just finding the product. So we're going to go straight from what it told us on the last page. So R1 times R2 times cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. 3 times 2 is 6. 1/4 pi plus 3/4 pi gives you just pi. Again, from your unit circle, or you can use your cheat sheet. This is pi. That is at -1, 0. Cosine is your x coordinate. So that's -1. Sine is your y coordinate. 0 is going to cancel out right there. And then 6 times -1 is -6. So your product is going to be -6. Find the product of Z1, Z2. So you're going to do your two outsides of your R, 2 times 8. You're going to do cosine theta 1, 2 pi over 3, plus theta 2, which is 11 pi over 6, plus I sine, same thing, 2 pi over 3, plus 11 pi over 6. You get 16 times cosine. 2/3 will change into 4/6, which gives you 15 over 6. And we'll just write this here so you can see it. And we reduce that by 3, we get 5 over 2. So 5 pi over 2 plus I sine 5 pi over 2. I'm a cheat sheet for a minute so I can show you guys exactly what I'm doing. So from the last one, I'm gonna go back up for a minute. Your pi, again, we're using our cheat sheet. The problem is we don't have our 5 pi over 2 on here. So what do? I can just drop it into my calculator. Let me pull that up for you guys. If I get a text or something, I'm sorry, I'm using my phone. Okay. We're in radian, so I need to make sure I'm in radian mode. Cosine 5 pi over 2 gives me 0. And then sine 5 pi, sine 5 pi over 2 gives me 1. Don't forget your I with your sine. So when I multiply this together, that will just give me 0 plus 16i, which gives me 16i. So that was multiplying. The next thing we're going to do is dividing. So we're going to use that quotient rule that we've already learned. Remember, it's the same thing, except for you're going to divide your two numbers. So we have 24 and 8 that we're going to divide. And remember, instead of addition, it's subtraction now. So cosine 300 minus 75 plus I sine 300 minus 75. 24 over 8 is 3. Cosine 300 minus 75 is 225. I sine 225. If we look at our cheat sheets, 225 is here. Our coordinate is both negative square root of 2 over 2, so you can't really mess this one up. Cosine is your x coordinate, negative square root of 2 over 2, plus negative square root of 2 over 2i. And then we're going to distribute our 3 in. So negative 3 square root of 2 over 2 minus 3 square root of 2 over 2. So again, same thing. Right? Powers of complex numbers. The trigonometric form of a complex number is used to raise a complex number to a power. To accomplish this, consider repeated use of the multiplication rule. So z, just regular z, was r cosine theta plus I sine theta. To do z squared, I'm going to just go ahead and write it out for you guys. It's going to be r squared and then cosine 2 theta plus I sine 2 theta. They did some work in your book to get here. I'm just going to give it to you to save a little bit of time. Z cubed would be r cubed, and then you would just change it to cosine 3 theta. Same thing for fourth. So r to the fourth cosine 4 theta plus I sine 4 theta. And you would continue just like that all the way down. So what this does is this pattern leads to de Moivre's, I don't know really how you say that, so I'm just going to go with that theorem, which says if z equals r times cosine theta plus I sine theta is a complex number and n is a positive integer, then z to the n is going to equal r to the n times cosine n theta plus I sine n theta. Two more pages, guys. We're almost done. We're getting there. Finding a power of a complex number, use that theorem to find this to the 12th. So the first thing we're going to do is find r. And remember the way that we do that is we plug our a and b into the Pythagorean theorem or the distance formula, whichever one you want to do. So we get the square root of negative 1 squared plus the square root of 3 squared, which gives us the square root of 1 plus 3. Remember, square root and the square cancel out, which gives us the square root of 4 or 2. Then you have to find your degree or your theta. It can be radians as well. Remember, it's going to equal b over a, which is your square root of 3 is your b, over negative 1 or negative square root of 3. So remember, we have to look at what quadrant it's in. So if we're doing negative 1 square root of 3, we're going negative 1 and a positive square root of 3. So it's in quadrant 2. When we look in quadrant 2, we're going to get this one because this one's going to give you the negative square root of 3. Okay. Square root of 3 over 2. If we did this one, it would give you 1 over the square root of 3. We want this one. So 2 pi over 3 theta is going to equal 2 pi over 3. We're going to write it in trig form. So z is going to equal r is 2 times cosine theta plus I sine theta. And then by the theorem, we're raised to the 12th power. That's what it told us right here. So that means we're going to do 2 to the 12th times cosine 12 times 2 pi over 3 plus I sine 12 times 2 pi over 3. In your calculator, put in 2 to the 12th, you get 4096. Again, all calculator. 12 divided by 3 is 4. 4 times 2 is 8. So cosine 8 pi plus I sine 8 pi. When you put these in your calculator, cosine 8 pi, and I'll show you cosine 8 pi, you get 1. Sine 8 pi, you get negative e to the negative 13. That e negative 13 means that you're going backwards 13 places with the decimal. That is definitely giving you a 0. So it's just super exact. So this is 4096. Cosine was 1. This was 0. 1 plus 0 is 1, which gives you 4096. All right. Roots of complex numbers. Recall that a consequence of the fundamental theorem of algebra is that a polynomial equation of degree n has n solutions in the complex number system. So the equation x to the 6 equals 1 has 6 solutions. And in this particular case, you can find the 6 solutions by factoring and using the quadratic formula. And I know that we don't want to do that, but we can. That's what it says. You can find them. So x to the 6th minus 1 equals 0. We can factor into x cubed minus 1 and x cubed plus 1. When we factor perfect cubes, it's the cube root of the first, same sign. So cube root of the first, same sign, cube root of that. Square the first cube root. So square the first one, x squared. Change the sign. Multiply them together. 1 times x is x. And then square the last. 1 squared is 1. So if we do it again, x cubed, the cube root is x. The cube root of 1 is 1. So square the first one. Sorry, our first factor is what you see, x plus 1. Square the first one, change the sign, multiply them together. 1 times x is x, and then square the last. We can solve these fairly easy. X equals 1 and x equals negative 1. But the other two, since they're not factorable, you have to use the quadratic formula for these. So these are not factorable. You have to use quadratic formula. Remember, quadratic formula is x equals negative b plus or minus big fat square root b squared minus 4ac all over 2a. To save you time, I'm going to go ahead and tell you what your two answers are. For the first one, we're going to have a negative 1 plus or minus I square root 3 over 2. And for the second set, you're going to have the same thing, just opposite sides. 1 plus or minus I square root of 3 over 2. Each of these numbers is a sixth root of 1. In general, an nth root of a complex number is defined as follows. So we have the definition on the next page. Again, last page, we're almost done. The definition of an nth root of a complex number. If we have the complex number, u equals a plus bi is an nth root of the complex number z, when z equals u to the n, that would mean a plus bi to the n. Finding nth roots of a complex number for a positive integer n, that complex number, that z that we found earlier, r times cosine theta plus I sine theta, has exactly n distinct nth roots given by z sub k equals the nth root of r times cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. Give me a second to write that down. So you guys know that we've been doing like our answers pi over 2 plus 2 pi or plus 2n pi. So that's basically what you're seeing right here. Instead of being 2n pi, now it's 2k pi. So k is like 0, 1, 2, all the way to the n minus 1. Right? Find all 6 roots of 1. So the first thing that we want to do is put it in trig form. So z equals 1 times cosine 0 sine 0. The second thing that we're going to do is define our n, which is 6, and our r, which is 1. So z sub k, we're looking for the 6th root of 1 of cosine 0 plus 2 pi k over 6. Again, we're just plugging into that formula right there. Plus I sine 0 plus 2 pi k over 6. The 6th root of 1 is just 1, so you don't have to write that. But then here, 0 plus 2 pi k is just 2 pi k. 2 over 6 is 1/3. So this actually simplifies to pi k over 3. Remember that k is going to equal 0, 1, 2, 3, 4, all the way up to n minus 1. Since our n is 6, we're going to go all the way to 5. So again, all the way to the n minus 1. And we're going to do this multiple times, and it's long-winded. How about that? That's better to say. So cosine 0, because no matter what I put up here, if I put 0, it's just going to give us 0 anyway, plus I sine 0 gives us 1. Again, you plug that into your calculator. Cosine 0 is 1. This one is 0. It'll multiply out. You have to do number 1. So we have to do this till we get to 5. So Z1 is cosine. When we plug in 1 times pi, we just get pi over 3 plus I sine pi over 3. Cosine pi over 3 is 1/2. And then sine pi over 3 is square root of 3 over 2. And don't forget your I with that. And again, that's from your cheat sheet. So pi over 3 is right here. Cosine is your x coordinate at 1/2. Sine is your y coordinate at square root of 3 over 2. So that's where these numbers are coming from. And I'm going to keep doing that. And I'm not going to keep showing you, but that's where they're all coming from. The next one, we're plugging in 2. So 2k, I don't even have my 2 on here, is 2 pi over 3 plus I sine 2 pi over 3. So your 2 pi over 3 is right there. Cosine is negative 1/2. And then 2 pi over 3, your sine is square root of 3 over 2. So plus square root of 3 over 2i. Now, remember that we did go sign these just a minute ago where we were right here. If you guys look at these two, we have positive and negative 1/2. So there's your positive 1/2 plus square root of 3 over 2. And here's your negative 1/2 plus square root of 3 over 2. Sorry, you can't really see that. So we're just finding this without having to use the quadratic formula. It takes a lot longer, but you can do it. So Z3, we're going to put our 3 up here. 3 over 3 is 1. So it's just cosine pi plus I sine pi. Remember, at pi, your coordinate is negative 1, 0. So you're just going to have negative 1, and this is going to cancel itself out. We got to do Z4, which is cosine 4 pi over 3 plus I sine 4 pi over 3. At 4 pi over 3, your cosine is negative 1/2, or your x coordinate is negative 1/2. Your y coordinate is negative square root of 3 over 2. Make sure you put an I there. And then the last one, Z5, is cosine 5 pi over 3 plus I sine 5 pi over 3. 5 pi over 3 is at the bottom, and it says cosine is 1/2, and sine is negative square root of 3 over 2i. So there's all 6 roots. Again, not done with quadratic formula. It's much easier to do it with quadratic formula. You thought quadratic formula was too long, but it does get worse. So decide what you want to do, like on your test. I don't care if you want to do it here in your homework and stuff. I want to see it like this, but again, on your test, I don't care how you found them. So find the 3 cube roots of z equals negative 2 plus 2i. So the first thing that we're going to do is figure out what our r is, because now we have a negative 2 plus 2i. There's no point in putting it in the z form just yet. We got to get that r first. So remember, we do the square root of negative 2 squared plus 2 squared, which gives us the square root of 8. We're going to look for our radian degree, whichever one you want to do. We're just doing radians. B over A is negative 1. Negative 2, 2 is in quadrant 2. So our theta is equal to 135 degrees. And again, you can do degrees or you can do radians. I don't care. Okay, it's up to you. All right. So then we can write it in terms of z now. We get the square root of 8 times cosine 135 plus I sine 135. And then we do our zk. We want the cube root of the square root of 8. So the cube root of the square root of 8 is going to be the 6th root. And again, that's just because it's the square root of 8. Cosine of 135. Remember that 2 pi up here at the top, we did plus 2 pi k. If we're doing degrees, we're not doing 2 pi, but we're doing 360 k. Over our n, we're finding the 3 roots. So that I sine is going to be exactly the same. Let's talk about it one more time. 135 degrees was what our theta was when we solved it. Remember, you can do tan inverse, and you're going to get 135. Instead of being 2 pi in radians, it's going to be 360 in degrees, and then times the k over 3. This is your general form. Remember that we need to find the 3 roots. So k is going to equal 0, 1, and 2 because that's 3 answers. So Z1 Z0 is going to end up being the 6th root of 8 times cosine 135 plus 360 times 0 over 3 plus I sine 135 plus 360 times 0 over 3. The 6th root of 8 is going to leave you with the square root of 2 times cosine 45 plus, I'm squeezing it in, I sine 45, which gives you 1 plus I. And again, just work that out so that you can see it. Z1, we're going to keep that, this 6th root of 8 is the square root of 2. So we're going to keep the square root of 2 on this one. We're going to multiply by 1 this time. So 135 plus 360 times 1 divided by 3 is 165. So again, don't stress out too much. I'm trying to do it so we can get done. Alpha y equals 135 plus 360 times 1 over 3 gives us 165. So I just wanted you to make sure where I got that from. I sine 165. When you put it in your calculator, you're going to get some crazy decimals. So square root of 2 times cosine 165. I need to make sure I'm in degree mode. And I get this crazy decimal negative 1.3660, which is perfectly fine. 1.3660. And then when I do square root of 2 times sine 165, I get a positive 3660I. And again, that's just put it straight in your calculator. And then the last one we need to do is Z2, so square root of 2. When you plug in a 2 here, so 135 plus 360 times 2 divided by 3 is going to give you 285. And then when I distribute my square root of 2, it's going to give me nasty decimals again, 0.3660. But this time it'll be minus 1.3660. So they're not very hard problems, but they are kind of a little bit longer. And again, if you get regular like 6 roots of 1, like the first one, it's easier to do a quadratic formula. But if you get one that's imaginary, then you're going to have to do it like this. So that's it for 6.5. Your homework will be posted in Canvas. Thanks, guys.